We'll start this video by having you practice some of the techniques that we've learned. We've got a polynomial limit and two rationals. And so I'd like you to pause the video, evaluate the limits, and then start the video up again to check your work. Starting with the first problem, we have the limit of a polynomial, and the limit of a polynomial, we just use direct substitution. We're going to substitute the -3 in wherever we see an x, and we'll evaluate. Evaluating, we get 26. So the limit as x approaches -3 of 2x squared minus x plus 5 is equal to 26. Number 2, we have the limit of a rational function, and again we get to use direct substitution. 10 minus 10 over 10 plus 10, that's 0 over 20, and 0 divided by any non-zero number is actually equal to 0. So here the limit does exist, it's equal to 0. At the last example, we evaluate the limit as x approaches 3 of a rational function by direct substitution. Substituting x with 3, we end up with 0 over 0. This is that indeterminate form, and you'll hear me say this over and over again. We have to do more work. And so the trick here is, since this is a rational function, we are just going to factor. Factoring gives us x minus 3 times x plus 1 over x minus 3. Now remember, until you actually evaluate the limit, you need the limit notation in there. Notice in the first step, I don't have the limit written in anymore because the limit of this expression as x approaches 3 is equal to the expression evaluated at 3 if we get a finite answer. So I don't have the limit notation in this example, but down here, in this step I mean, and down here I need that limit notation. So we will cancel the x minus 3's, and now we can actually evaluate. 3 plus 1 will give us 4. So we know the limit is equal to 4, but we also know that this rational function, that r of 3, does not exist. But since this is a rational function that has a common factor, we know we have. Now we've already answered the question. The answer is 4, but just to add a little more information, because you may be asked about this, that we actually have a whole when x minus 3 is equal to 0. You set the common factor equal to 0, so we get x equals 3 is where the whole occurs, and the ordered pair is going to be 3, 4, the value of that limit. And I'd like to graph this one on the calculator just to show you what this looks like. Again, we've got a rational function, so you'd expect some type of asymptotes. So pulling up the calculator and entering this expression into y equals using parentheses, doing a zoom 6, just a standard graphing window. And so our rational function actually just looks like a line. And when I trace on 3, hit enter, we see there's no value. What this means is there's actually a hole at 3. I'm going to drag this screen so we can look at it even further. Right, having dragged the graph over, what's really happening here is that when x equals 3, there is no y value. There's a hole in the graph. So the function is not defined. Right? So r of 3 doesn't exist, but the limit does exist. As x approaches 3 from either side, the function is approaching 4. So this rational function, and you may or may not remember this from pre-calc 1, that when you're asked to find asymptotes, you are always asked first to reduce the rational function as much as possible, because you're only going to get asymptotes from factors after you have canceled any common factors. Common factors result in holes. And so really the original function, x squared minus 2x minus 3 over x minus 3, is the same as f of x equals x plus 1, meaning that factor that was left, as long as x does not equal 3. So this rational function is, the graph is the same as the function of a line such that x cannot equal 3. And if I wanted to fill in that hole, the ordered pair that would fill that hole would be 3, 4. Now let's look at the properties involving powers and radicals. And we'll start with example 4 here. We're going to evaluate the limit as x approaches 25 of the square root of x minus 7. So as before, we're allowed to do direct substitution. This gives us the square root of 25 minus 7, or 5 minus 7 is equal to negative 2. And so the value of this limit is equal to negative 2. Let's try the next one. This is a fractional expression, or that involves a radical. And we'll start again by direct substitution. We'll have the square root of 1 minus 1 over 1 minus 1, which you can see again is giving us the 0 over 0. And so of course I'm going to say that you have to do more work. And in this case, there's another little, again, there's some algebraic manipulation that's slightly different from what we've done. In the rational function we factored. In the complex fraction we just simplified the complex fraction. And for a problem dealing with radicals in a fraction, we're going to multiply by conjugate. So we're going to do some more algebraic manipulation. So I'll rewrite the limit. Here we're going to multiply by the conjugate. This is the algebraic manipulation. We're going to multiply by the square root of x plus 1 over the square root of x plus 1. So the conjugate of a binomial, you'd have the first term would be exactly the same, and the second would just be the opposite of what the original is. What's nice about multiplying by a conjugate is that you use the sum and difference formula for multiplying binomials. If you have a plus b times a minus b, you get a squared minus b squared. So what's going to happen in the numerator is you would get the square root of x squared minus 1 squared, or just x minus 1. In the denominator, I'm going to ask that you don't distribute and you just leave it factored, x minus 1 times the square root of x plus 1. And you can now see why I wanted you to leave that factored, because we have a common factor here. Now since we have not evaluated yet, I've actually omitted something that needs to be put in, and that is the limit notation. We are still taking limits, and so I need my limit notation. So we have the limit as x approaches 1 of x minus 1 over x minus 1 times the square root of x plus 1. The x minus 1's cancel. We now have the limit as x approaches 1 of 1 over the square root of x plus 1, and we can evaluate. Substituting 1 in for x, we get 1 over 1 plus 1, or 1/2. And so we have a limit that exists, which is 1/2, even though the expression or the function would not be defined at x equals 1. In the next video, we're going to look at limits of piecewise functions. So we'll end this one here.